So we're going to proceed to talk about waves. This is what we also covered in our physical tutorials. You can always join us. You can always contact me for your online tuition or physical tutorials, one-on-one physical tutorials. So we're going to be talking about the basic definition of a wave, transverse versus longitudinal waves, mechanical and electromagnetic waves. So let's begin with our basic definition of a wave. So a wave is a disturbance that carries energy through a medium without carrying matter along with it. A disturbance that carries energy through a medium without carrying matter along with it. And we are going to look at the common physical properties of waves that we use to describe waves. So this is what you can expect in this tutorial. We'll talk about the physical properties of waves, the common physical properties of waves. So what do we mean when we say that it's a wave carries energy but does not carry matter? So I'll illustrate using this this animation here. So I'd like you to focus on this this particle here. Okay, so you realize that as the wave moves along, that particle is not really going to be moving together with the wave. So in this case, if you look to your left there, the wave is moving to my right, so that's the direction of movement of the wave, but the particle is simply going up and down, in that circular motion. If you look at it from the top, you would see it going sideways, that is to your left and your right. If you look at this particle from the top, someone viewing this particle from the top would see it going left and right. So this would be similar to what is happening here. If you of matter, so it's going left to right, it's not really going along with the wave, which is going to my, in this case, it's going to my right. So this is what we mean when we say a wave does not carry matter along with it. It simply oscillates matter. So that kind of movement where your particle goes forwards and backwards, that's called oscillation. So it oscillates matter rather than carry it along with it. All right, so let's talk about the two types of waves. We have a transverse wave, a wave that oscillates matter in a perpendicular direction to the wave's motion. A wave that oscillates matter in perpendicular direction to the wave's motion. So we saw that in the previous animation. So let's also check this out, that the red dots are going to be oscillating up and down, and the direction of wave's motion is shown in this blue arrow here. So as you can see, the matter is going up and down. If you check for longitudinal waves, it is a wave that oscillates matter in a parallel direction to the wave's motion. So if you check here, our red dots as before, they are going in parallel to the direction of the wave's motion. So these are the key differences between your transverse waves and your longitudinal waves. So let's look at some examples of these waves. Transverse waves, we have strings in musical instruments. We have moving a slinky up and down will create for you a transverse wave. Then doing a wave at a sports game, it's a good illustration of transverse waves. And electromagnetic waves. And for our longitudinal waves, the common examples there are sound, okay, and also the slinky can be used to show longitudinal waves. So let's see these waves in these examples in action. So those are your musical instruments. The strings there are creating a transverse wave. So that is a good example there of transverse waves. So that's a slinky moving up and down. So a slinky can be used there to illustrate transverse waves. So that's another example. We can also have people doing a wave at a sports game. So that's a good illustration of what happens with transverse waves. We said they do not carry matter along with them, but they simply oscillate matter up and down. So each person there is like a particle of matter going up and down, but in doing so you see that they create a wave. There's a wave which is passing through them. So that's a good illustration of a transverse wave. Now when it comes to longitudinal waves, sound produces those waves. So that's the speaker there producing sound, and those dots around the speaker represent our air particles. So what happens is that the particles will be going back and forth, and they are not really going anywhere. So that's oscillation, but the oscillation here is in parallel to the waves direction of motion. So this is what we mean. These are the key differences. So let's move on. So let's talk about let's also see the slinky being used to illustrate here our longitudinal waves. So if you see that, just know that the slinky is being used in this case to illustrate our longitudinal waves. Okay, now let's talk about mechanical waves versus electromagnetic waves. So these are the other two categories that our waves can fall into. A mechanical wave is a wave that requires a medium to move through, a medium such as water or air, and it oscillates matter. We saw that these mechanical waves can be transverse or longitudinal. We have another special group of waves which are called electromagnetic waves, and this is a wave that moves through empty space or a vacuum, and it's created as a result of the vibrations between electric fields and magnetic fields. And all electromagnetic waves are photons or particles of light, and all move at the speed of light. They all move at the speed of light, denoted there by lowercase c, 3 times 10 to the power 8 meters per second. That is the speed of light. So all these electromagnetic waves move at the speed, and they are going to be different, of course, between these electromagnetic waves, and there are only going to be differences in wavelength and frequency. So we'll look at these properties next. Okay, so it's important to note here that we can show a wave on a displacement distance graph. So on this graph, a wave is going to look like this, and there's parts of the wave that you must be able to label. For example, that distance there is the amplitude of the wave. So this is the total distance that the wave is going to be able to displace that particle of matter that you saw from a position of equilibrium or from a central position. So that is the amplitude of a wave, and the larger the amplitude, the more energy the wave carries. So all those distances are amplitude. Okay, so maximum displacement from rest or a central position is what we mean by amplitude. And then you must know that there is something called wavelength. So what is wavelength? The distance between any two consecutive points that are in phase, or rather this is the distance between any two consecutive these are called peaks or crests, and these are called troughs. So any two consecutive peaks, any two consecutive troughs, that's going to be a wavelength. You can also measure wavelength from the central line here, from here to here, and you should avoid the common mistake of measuring only from here up to here and think that's a full wavelength. That's not a full wavelength. It has to end here. So those are the three positions from which you can measure your wavelength. So another graph that can be used to show the properties of a wave is the displacement time graph, and from here we can learn about the period of a wave, and I'll talk more about the period of a wave, what it is. But here, just briefly, it is the amount of time taken for one complete cycle, that is to move, for example, from the peak here to the peak here. That is your period, the time required to move from that peak to the next peak through. So those are some of the properties. So that's a period there. So you must be able to define this term. So let's do this in the next video.